Hello, I'm audible.
Good afternoon, everyone. I'm excited to welcome each one of you present in this speaker session conducted by the Innovation Cell in collaboration with Center of Space and Interplanetary Exploration, cosigned NIT Raipur. I would like to acknowledge the presence of our esteemed guest speaker, Dr. Yogesh Pratap Singh, and Dr. Saurabh Gupta sir, our faculty in charge, Innovation Cell.
Ladies and gentlemen, it is our immense pleasure to welcome Dr. Yogesh Pratap Singh, our distinguished alumnus. After completing his bachelor's degree in mechanical engineering from our very own institution, he went on to pursue his Ph.D. and MTech degrees in Indian Institute of Science, Bangalore, where he is a postdoctoral fellow in the I3D lab at IISc, working under the mentorship of Professor Pradipta Biswas. Dr. Singh's research interests span dynamics, robotics and design, mechanism design, vibrations, and control systems. He is also a recipient of the prestigious Prime Minister Research Fellowship. We are honored to have him share his expertise with us today.
And in today's session, Sir will be delivering an insightful technical talk on his PhD work, a very interesting topic that is dynamically isotropic Gauss-Stewart platform for microvibration isolation in spacecrafts. Through this session, we hope to gain a deeper understanding of the latest advancements in robotics, design, and space technology, and the importance of research in driving innovation.
So get ready to experience the wonders of science and technology as our esteemed speaker take you through this journey.
And before we start today's session, I would request everyone to kindly turn on their cameras. I would now like to hand over the mic and the virtual floor to Dr. Singh to enlighten us and give us the knowledge about today's topic. Sir, over to you.
Thank you, Mokshita and Anshika. I hope I'm audible.
Yes, yes.
Yeah, thank you. So thank you to NIT Raipur again, and special thanks to Innovation Cell and Center of Space and Interplanetary Exploration. Uh, I mean, when I was in my undergrad days, I always wished we could have something like this. But seeing you all fulfilling your dreams, and in fact, my dream also is, uh, I'm very happy for that. And thank you to Saurabh Gupta sir, who is also my senior at ISC, and very happy to see that he's taking initiative among all faculties. And wish you all good luck that you take this initiative forward. So as we begin this endeavor, can I share my screen? Yeah, you can see my screen.
Yes, sir. Yes, sir.
Yeah. I hope my slides are visible.
Yes, it is visible.
Yeah, so again, good afternoon all. And as you all begin your endeavor in space technology, so I am Yogesh Pratap Singh, as they have already introduced, and I recently joined as a postdoc in ISC. Before this, I did my PhD from Robotics and Design Lab from ISC under the mentorship of Professor Ashitava Ghosal, who is a very well-known person in robotics in India. So, though we are going to, the topic of my talk today is dynamically isotropic Gauss-Stewart platform for micro vibration isolation in spacecraft. But since it's a PhD topic, I am aware that you all are from different backgrounds. So we'll try to cut the topic as short as possible, and we will also see some other projects and space environment that we have in ISC, because as I told you, are going into a new endeavor of this Center of Space and Interplanetary Exploration. So if you are not from mechanical background or control systems or electronics background, I'll still try to. If you had not seen, you should surely go and watch how everything in Bangalore took shape. So basically, just to brief, in 1940s, Vikram Sarabhai was doing was World War II happened, and then he has to come back to India, and then his father research paper to uh, C.V. Raman, who was then the director of IISc, and later he got selected in IISc, and then Vikram Sarabhai came, worked under Homi Bhabha, and then from IISc everything was started. During that time, Bhabha also established a cosmic ray center in IISc, so he was a professor here. And then, as you all know, that in 1962, after everything, Sarabhai was appointed as the chair of the Indian National Committee for Space Research, and which eventually in 1970s around converted into ISRO. So a very interesting story. One of the big reasons of ISC being a hub of space technology is its location. It's very close to. I mean, we have 6 to 7 centers of ISRO in Bangalore, but the ISRO headquarters is very near to ISC, and the reason is that when Satish Dhawan I think passed away in 1970, Indira Gandhi, then the Prime Minister, called Dhawan that you should take up ISRO. Then Dr. Dhawan gave two basically conditions, that he will join ISRO on two conditions. First, that he will not be asked to leave the director of IISc, because Dr. Dhawan was the Professor Dhawan was director of IISc during that time. So he told that I will be director of IISc because I don't want to leave academia, but meanwhile I can serve as a chairman of ISRO. And second condition he put that because he don't wanted to walk too long, so he told that the headquarter of ISRO should be next to IISc. So for the same reason, IISc and ISRO are closely related. And as I told, there are many good research that is going on, in collaboration. And if in future you come to IISc, you can. It's a very good chance of recent Professor. He remember to fail to that he had no doubt that Chandrayaan will safely land on moon. Then next lab to me is another lab of Professor Alok, who all take, basically they have a simulated Mars and moon soil, and out of that they make bricks. And in the future, if you go to, say, the basic idea is, just if you I want to give you a number, to take a single kg to space means 400 kilometers, say, just the orbit, it will take you 6 lakh rupees in GSLV. Just I am giving an estimate. So if you want to take a single kg to moon, you can imagine how much cost it will take. So we cannot take the bricks from here or anything from here and colonize on moon. So what we can do is utilize the say the soil of the moon or the soil of the Mars, and develop develop a brick or any rock or something like that, which is able to sustain the pressure and all the temperature gradient. So they are working on this project. So there are many such interesting projects. uh, ISC, as you all know, that we are as India is the next big mission for India is the Gaganyaan mission, where we are sending astronaut to space. So for around 1 year, whole of India was kept, around 3 years, whole of India was kept, that who are there, kept in dark, that who are their astronauts. And apparently last, I think this year only, it was released 9 months back, that all the 4 astronauts are actually uh, also an MTech student of IISc. So they are all pursuing the MTech students of IISc. And one of the astronauts, which is Captain Ajit Krishnan, who is also our lab member, so I3D lab member, he works in our lab. And during his PhD, so he also, you can see, he developed a simulator for his MTech research work. So in short, they are all fighter pilots, but they are doing sponsored MTechs from here. So in every year, if we have around, say, 5 to 6 astronauts to 6 Air Force and Navy people who get sponsored to their, and they are those people. So it's a very proud moment for us. So obviously, when you come in an environment like IISc, you interact with all those big guns who are contributing in this field. As you can see, Ajit, who is also my lab mate, and then this is Prashant sir, who is right now in US for the Axiom 4 mission. Is undergoing training. And Angad sir, I think Saurabh sir also is was in ISC 2 days back, and he also came to watch our cricket match. So you can see Angad we are playing with all. So you have some beautiful interaction. As you can see, this is ISRO chairman. This is a proud moment where my mother and father they can meet. This is Dr. Unni Krishnan, who is leading Gaganyaan mission. This is Dr. Kiran Kumar, who was ex-ISRO chairman. So we have all such interaction, and the purpose of showing these slides to you is that when you get a good environment, you obviously flourish and interact with people you want to work around, and basically the projects you want to work around. So this is the theme of showing this all. So I'm audible. I hope I'm audible. Hello. So yeah, as far as my journey to IISc is concerned, I was also at the same place as you were, but I joined. I mean, the biggest decision of my life was I joined NIT as a computer science student, and then I got the admission in computer science and engineering. And after 2 days, there was a special round there where if you want to change your branch internally, swap it with someone. So I know many of you, it's a very unconventional practice, but then I internally slided to mechanical engineering. And I think that was a very good decision in my life. I feel so. No harm to computer science. And during this process, when I took mechanical engineering, to be very honest, I always wanted to take aerospace engineering. Like many of you who are enthusiastic in this field must be want of aerospace engineering. But as you all know that it is only in, I don't know, but in my time it was all only in 5 IITs or 6 IITs. So I also worked hard for engineering, but the sad part was maybe some 12-13 marks more, or some 3,000 to 4,000 rank in aerospace, I would have got aerospace engineering. That time I used to be very sad for the same that I didn't get aerospace engineering. But today when I look back and after going through the process, I would tell you that not getting aerospace in IIT was the most successful failure of my life. So why I tell you the most successful failure is because that time there was no one to guide me. But when I went into mechanical engineering, I ultimately realized that when you take a core branch, be it mechanical, any core branch, you can always, aerospace or naval or automobile, or always a subset of, I hope what is subset, you understand the set theory. So they are all the subset of mechanical engineering. So when I took mechanical engineering, I told that, okay, I can't take aerospace now, but I can, and I align myself to work for aerospace engineering and the dreams that I have seen for myself. So you can see throughout my journey, like people around me were going for automobile internship, or what a conventional mechanical engineering will do. They will go for power plant, they will go for oil. But I was very clear that I will build my profile in aerospace engineering, and mechanical is a good branch to go through because it's a very fundamental branch. So initially I worked with drones in my initial years. Then I went did my internship in HAL in helicopters division. Then I worked with aircraft division. Then I got a exposure of aircraft. Then I worked with National Aerospace Lab in fatigue and structural group. And then I worked in ISRO R&D in my 6th semester at LPSC, that is Indian Space Research Organization. LPSC is one of the centers in Kerala. And then I got Prime Minister Research Fellowship, in which I directly joined IISc. So just a brief, I'll just tell you only my aerospace projects. I did many projects, but during my BTech journey in and at NIT Raipur when I was doing internship in ISRO. You will still see this project as a, when you open the list of project in ISRO, it's still there. So I did, you can see I designed a vibration setup for ISRO, and I think they have, during my time, I gave the design. As you can see, this is the top view, side view, but now I think they have built this setup. I don't have a photo, but I think they have built this setup. And during my time, I worked around 1.5 months, and then I worked on the design of this. So basically, the application of this was to understand the vibration characteristics of a fluid line emerged in fluid of liquid stage of launch vehicle. So we have liquid stage in a launch vehicle, as you know. So it's C25 stage in GSLV Mark III. And in that, as you know, there are feed lines, basically the pipes which goes inside the liquid stage. So when the pipe goes inside a fluid medium, and when rocket is in motion, it will vibrate. So to understand that characteristics, this setup was built. One of our very famous project, and I think in my initial years, which I really I so you can see a lot of people acknowledged in this project. This is because people from NIT, people from IISc, and people from ISRO have worked on this project. So this was design of a common bulkhead dome for cryogenic stage, and this work I started during my BTech days in my end semester, and then eventually it continued in the first and second year of my PhD. So around 2 years remotely I worked on this project. And in this project we showed that we can, in GSLV, we can save up to 475 kgs. So you can understand, if you save, as I was telling, that if you want to carry 1 kg of payload to space, it will save 6 lakh rupees for you in GSLV. So you can understand what is 475 kgs. And the basic idea, if you see the current GSLV structure, if you see, this is a LS2, means liquid hydrogen stage. This is the liquid oxygen stage, and currently it is linked by intertank structure. So the entire idea was that instead, because these two liquid are like, say, liquid hydrogen, if you see, it's at 19 Kelvin, while liquid oxygen, sorry, 77 Kelvin, while liquid oxygen is at 19 Kelvin. So the pressure gradient between these two is so much that it is normally kept at a separate containers, and that is why this interstage is required. But if you design your dome and with a particular strength and particular say insulating materials, so you can eliminate this entire stage and save mass. So this was a brief idea of the project. Will not go in deep in this project. And this project, I mean, it was one of my initial project, though I did it in my BTech. You can see we had around 3 publications from this. One is going to be published by ISRO, one is published by DRDO, and 2 best paper we got from this, including one from DRDO, where we were awarded by ex-ISRO chairman. And it was in a lot of national and local newspaper and national media is what highlighted. So this was one of the space project that we did during the NIT. Then my journey came to IISc, and now when I came to IISc, I came through Prime Minister Research Fellowship, and I joined as a direct PhD student from NIT. And what I wanted to highlight here is that that time when I joined as a PhD student, I had option of all the IITs and all the IITs and aerospace plus mechanical plus design. So I had the option of going to aerospace now, but I was sitting with Sanyal sir, and this is where, you know, we often criticize our professor. We take snooks but I was sitting with Sanyal sir, and out of his experience, Sanyal sir told me that I asked him one fundamental question, that, sir, now I have option of aerospace also and mechanical engineering also, and I have in all the IITs and IISc. What should be my preference? So he told that if you again take mechanical, you can always work on aerospace, and mechanical is a fundamental branch. So my option was mechanical and then aerospace. So even though now I was getting aerospace, I didn't go for aerospace because core branch is a core branch, and whatever you want to work with, the fundamentals, you should always focus on fundamentals. So when I was talking to Sanyal sir, I also asked him one question, that which is the one professor which I should go and approach, and he should be my advisor at IISc. And he took the name of Professor Ashitava Ghosal. And luckily, when I came here, I got Ashitava Ghosal sir as my professor. I worked with an ISRO project during my PhD, And as you can see, this is my lab group, Robotics and Design Group, though I am no more part of this group because Ashitava sir is also retired and I also left, I mean, did my PhD from here. But this is a very good lab because here, like if you see everywhere you go in any IITs or something, and in most of the robotics lab, most of them work on robots which they are not developing from scratch, they will buy from somewhere. But from in our lab, all the projects you see from 1989, when professor returned from Stanford, so he studied from Stanford, and you can see all this robot which has been designed in our lab, they are designed from scratch, whether be quadruped robot or some endoscope or soft robot. Everything that we have done in our lab, snake type robot, everything is designed from scratch. So this is where, so as you can see, what research that I am going to talk now, we'll go into the technical part. So the research which I am going to talk was covered by IISc Media, and it is published in a reputed journal called Mechanism and Machine Theory. And basically, more than the topic, I want to take you through the design process. I want to tell the difference when you do a project and when you do a thesis. So basically, in thesis, you study everything in a generalized way, not like a project where you are just implementing something. So we'll just begin with the technical topic. So coming to my research topic, and spacecraft, there are micro vibrations up to 250 hertz. So I hope you know what is hertz. This is a unit of vibration. And what happens in spacecraft, we have reaction wheel, momentum wheel, cryocoolers, say in satellite, all these components are present, and these are basically reciprocating or rotating in nature. So because of that, say in this table, I keep the table I am giving the talk, if I keep some rotating device, entire table will shake. So because of that, any camera that is mounted on the spacecraft bus or any sensitive equipment, there are many payloads, as you know, so they will also get affected. So basically, these micro vibrations will deteriorate the performance of optical payloads. So as you can see, this is an image without isolation. So if you are not isolating it, the vibration, if you are not isolating the vibration, it will be blurry. And if you are, this is what we desire. So basically, this is in terms of camera, but there can be other sensitive equipment. The overall goal is to isolate our equipment. Also during launch, during launch also we have high quasi-static load. The load is not 1G that we generally experience, it's 10G. So along with this vibration isolation from 0 up to 250 hertz, we have to also see that it is able to, means if something is say 1 kg in weight, it will not be 1 Newton, it will be 10 Newton because it's 10 kg. So now what we can do, the first thing is there are various vibration mitigation strategies. Like what you can do is say you have your spacecraft bus. So first thing is you either isolate all your noisy components, noisy in the sense things which are vibrating or reciprocating, you isolate them. Or the other thing is that from you isolate your payloads, means sensitive payload. So either if you want to keep p, you remember there was something natural frequency which we used to write as under root k upon m, if you remember, omega equal to under k upon m. So this is the natural frequency of the system, and when you excite this with this natural frequency, it is going to go in the state of resonance or the high amplitude. So basically, this is a, if you see spring mass damper, this is a single degree of freedom system because it always oscillates along one direction. But in a degree of freedom system, there are 6 natural frequencies. So how does it works is, I'm just briefing it for non-mechanical people. So there is something called amplitude and there is something called frequency. So suppose I give a unit frequency, a unit displacement here to the base. This is the base, fixed base. I give a unit displacement here at say nearly 0 frequency. So this curve will start from 1, and then the amplitude will go to maximum at resonance and it will then isolate. So you can see this is the resonance point. This is under root k by m for a single degree of freedom system. So basically what it is meaning to say, you give at the base, you are giving 1 and you are recording what is the output, and at resonance it will go to maximum, but after a certain point it goes less than 1. So you can see this is root 2 times omega. So if resonance is omega, this is root 2 times omega. And what you have to remember is after root 2 time omega, means after some point, after some frequency, the amplitude is less than 1. So if you are giving an amplitude of 1 in your base, okay, and there was no damper or something, this would have also oscillated by 1. But if you give, if you operate in this region, say this region, you will get amplitude less than 1. So coming back to our slide, so you can see here that what we wanted, that all 6 natural frequency are at one place. Why we wanted? Because when we see a conventional Stewart platform, conventional, just a second. You see, this is a conventional Stewart platform. See, this is a resonance curve for X mode, say X direction mode. So after some frequency, root 2 omega, it is going less than 1, which we wanted to operate. But what is the problem? It is this region of isolation is deteriorated or destroyed by resonance peak of other degree of freedom. Means basically you want, basically there are 3 roommates, and you basically in say in NBH there are 3 roommates. I think in new boys hostel you have 3 roommates, and they have different sleep cycle. So someone wants to sleep, say study in the morning, but his roommate who sleeps late in the night, then he will do noise and everything in the night, so this person will get disturbed. I hope you got my point. So the best solution of this would be that all of them, they wake up at a similar time and sleep. The sleep cycle is consistent, and in this way all 3 can study effectively. So the whole idea is, why not bring all this curve, all the 6, this is only for, but all the 6 modes, we are going to all the 6 mode, the peaks of all the 6 mode we are going to bring at one place. So there are 6 degree of freedom. Each degree of freedom will have will corresponds to one of the major modes, and all of them we are bringing at one place. Now why we are doing so? If we bring all the resonance peak at one place, it will be easy to tune dampers for vibration isolation, because whenever you tune any damper, you can tune the damper for a particular band frequency bandwidth. So you can see here, this is corresponding to different frequency bandwidth, this is corresponding to some different frequency bandwidth. So if you bring all this natural frequency at one over this other, everyone will come to a same place, and you can tune the dampers for that particular bandwidth. And if you are from a control system background or from electronics background, though I have not worked in my PhD in this part, but it's a good future work that you can see this is a multi-input, multi-output system, means 6 degree of freedom, 6 input and 6 output, and they are coupled. But when you design it in such a way where all 6 natural frequencies are equal, you decouple this 6 degrees of freedom into 6 single degree of freedom system. So we had a 6 degree of single system, MIMO system, we converted into 6 CISO system. So now instead of any complex control system that you employ, you can make use of a very simple control system like PID or something, and then it will give you a good result. So this is only possible in when you use a dynamically isotropic design. And what I mean by dynamically isotropic design is the first 6 natural frequency of the system is same. So I hope you got the point. And by achieving dynamic isotropy, you are also achieving static isotropy. And by static isotropy, we mean that it is behaving uniform in all 6 directions. So if I am pushing it from any direction with a say force of 1 Newton, this platform will give this, say it is giving displacement of say 2 centimeter. So in any direction you push this platform with 1 Newton force, it will always displace by 2 Newton, 2 centimeter only. Same for moment also. So this is a isotropic configuration. I hope you know the meaning of isotropic. And but the problem is that we can never achieve this dynamic isotropy or the phenomena of making all 6 natural frequency equal with a conventional Stewart platform. So just to explain you the term of isotropy, I mean we use in material science also and in most of the field. Isotropic basically means you have a homogeneous behavior of something, that is called isotropy. So homogeneous behavior of a certain kinestostatic property which is exhibited by robot in all direction. So if robot is exhibiting uniform behavior of a certain property, we call it isotropy. So if it is geometrically isotropy, we call it geometrical orthogonality. If it is isotropy in terms of velocity. If it is giving uniform velocity in all the direction, it is kinematic isotropy. If it is uniform in stiffness in all the isotropy, it is stiffness isotropy. And if it is in terms of force, it is static isotropy. So this all people have explored in the past. And if you want to go for applications such as you want a precise motion of telescope or scanning microscope, something like that, or some fabricated circuits, you can go for this design. But if you want something like a vibration isolation problem, we should always go for a dynamically isotropic design. So I will go through the process. Any doubt up till now, if anyone? So the whole idea is, if you can see, this is the schematic diagram of this. The whole idea is that the base of the platform is mounted to the spacecraft bus, you can see, and on the top platform, payload will be there, or your noisy component. So I told you there are two approaches: either you isolate the payload from the disturbing sources, or you isolate your disturbing sources from the payload. So you can keep your payload on the top of this platform. These are your 6 legs. Now this is, as you can see, this is a very unique design, because in our conventional design there was a single radius. All the mounting points you see, they are on the single radius, while if you see, this is a 2 radii toward platform. The mounting points here, you can see, they are on 2 radii. So here you can see there are two types of leg: one is blue and one is leg. So this is called a 2 radii or a modified Stewart platform. And through this Stewart platform, we can achieve dynamic isotropy. So this is the way of achieving dynamic isotropy. With one radii we cannot achieve. So this will have a mobile platform. Basically the top platform will be mobile. A fixed base, which will be fixed base, basically means which will be mounted on the spacecraft bus, from where the vibration will be propagated. And there will be legs which in active control will be actuator, and in the passive control vibration will be dampers. So whatever you are working out. Now the challenge is that it's not always that you choose some random configuration and you will get a dynamically isotropic configuration. You have to design this system to be a dynamic isotropy. So you can see there are variables, like you take variable x, y, z. So you take here, you can see there are radius variables. So the bottom outer radius is called RBO, the bottom inner radius is called RBI, so top radius is called RTO, the top radius is called RTI, inner one. So in this way there are many angles also, how they are related to the global axis. Then there is height variables. So these are all design variables, and for some specific values of these design variables only, we are going to get dynamic isotropy. So it's specific in the sense there are multiple solutions to this problem, but it does not mean that every time you take a 2 radii Stewart platform you will get dynamic isotropy. So we need to work out this problem to find what is the solution to this problem. And just in the bottom platform, there are all this bottom platform, it is connected through a spherical joint, and the top platform you can connect it through spherical or universal joint. And why I'm telling regarding the joints, because in synthesis of mechanism the joints play a very important role, because to get a 6 degree of freedom you have to use this type of joint only to allow your platform to move in 6 degree of freedom. So all these 3 legs, there are 2 types of leg. Again I am repeating, one is blue, you can see blue ones which are in the outer radius, and they are, each of these leg are rotated symmetrically about the center. So these blue legs are rotated by 120 degree from each other, as you can see, A1 B1 A2 B2 and A3 B3. And these black ones similarly are rotated by 120 degree. So there were few studies in the past, but very few research group have worked in the past, and they all gave some mathematical equations. I mean, not the solution, the mathematical condition. They showed some geometrical conditions, but none of them, they did some brute force optimization or solved some non-linear equation using computer. But none of the research groups have given closed form solution in the past. So we worked, I mean, the first thing is to do a good literature survey and research and identify the research gap. So during my initial days, when I was going through the literature review, I concluded that a consistent analytical closed form solution for the design parameters, I mean, for all these design parameters, we need to know what is the closed form solution, basically the formula, what we say in layman language. And none of the research group have ever built a Stewart platform which was dynamically isotropic. So there are Stewart platform in the past for many applications, but a dynamically isotropic Stewart platform for vibration isolation was not built, and also a dynamically isotropic Stewart platform with more than 6 lakh. So this is a Stewart platform with 6 lakh, but later we extended this study for more than 6 lakh, which we will see later. So my entire PhD, I mean, this is a part of my PhD, but it was first is I took the problem in an analytically, which is a very, I mean, fundamental problem. I mean, I'm going to write equation in a 6 DOF. I'm basically working out a 6 DOF dynamics problem. So the closed form solution, this is the first part of my PhD. Once I got the result out of that, then we go for a FE simulation, what you called as a simulation on computation. So whether it's giving the same results or not. So we did the simulation part to verify whether our analytical approach was correct or not. And then we went into our final design and experimentation, which was done at ISRO. And the whole purpose is probably it is intended to fly in actual aircraft in the near future. So it has given some encouraging results, and we hope that it will go in the spacecraft very soon. So you can see it's an entire journey, and we have been able to validate all the I mean, writing the equation, then validating it in FE software, and then experimentation is a very tough task. I'll not go into detail of the formulation because I mean I understand your background, but overall, if you see, there is something called a B matrix in robotics or a Jacobian matrix in robotics, which basically relates your joint space to task space. So by joint space, what I mean is that say you have a robotic arm, so XYZ, whatever you calculate in terms of global movement, XYZ, your end effector of the robot or your tool, or you are welding then the tool. So the XYZ, the end effector movement is basically the task space, which you can see here XB, YB, ZB, and how it is related to the joint space movement. Joint space means how your each actuator is moving and how based on each actuator, how your global robot is behaving. So they are related by a force transformation matrix or a Jacobian matrix. And it is given in terms of, you can see this is a unit vector. SI is a unit vector in say one of the leg. So same way in overall, just in brief, this B matrix is related to the geometry of this robot. And then we did the formulation, we calculated the stiffness matrix. So what is a stiffness matrix? So we don't know what is the stiffness matrix of this robot in the overall space, but all we know is in each of the leg, the stiffness of the each of the leg is K. So if each of the leg is having K stiffness, say all these 6 legs have K stiffness in their axial direction, what will be the stiffness of this robot in global direction? That is XB, YB, and ZB. So that is given in terms of force transformation matrix B. You can see BB transpose and the axial stiffness of each of the leg, how this is related in global coordinate system. Same way we construct the mass matrix in terms of mass of the payload and moment of inertia of the payload, and we construct M inverse KT. So if you remember in our formulation simple spring mass damper, what we used to write K by M under root. So omega square was equal to K by M, if you remember simple oscillation motion or whatever you studied in IIT JEE. So it is quite similar. This is just in 3-dimensional form that I am writing M inverse KT. So we got a G matrix, just the formulation part. This is whole G matrix. And the entire idea is that like you worked in terms of under root K by M, here we will not have only one omega. Here we will have 6 omegas, omega 1, omega 2, omega 3, omega 4, omega 5, omega 6, because we have 6 degrees of freedom. And the entire idea is to make all these natural frequencies equal. So you can see this will be equal to omega square. So whole idea what we had is to make natural frequency equal. And if you remember, if you recall your just basic mathematics which you studied in your M1, M2 or M3, is that if you calculate the eigen value of this matrix, this will be equal to your omega square. So we calculated the eigen value of this matrix. I hope you remember A minus lambda I, or if you, for a moment I did not use A minus lambda I, what I did is I diagonalized this matrix. If you diagonalize a matrix, if it's only in the diagonal form, then the diagonal elements of the matrix will be its eigen value, and that is what I have used. And you can see all the diagonal values I have equated to omega square. So this is just the formulation part. If you have not understood, nothing to worry. And as I told, there are two types of leg. If you remember, one blue type I showed, which were 3 numbers, and one was black type, which was which was 3 numbers. So they are related to each other by a leg length ratio. So say some blue one was say 1 meter and black one was say 0.5 meter. So the ratio will be 1/2 or 2. So this is related by a parameter called known as variable a. Just I am telling because it will be used many places. So this is a complex formulation, the set of transcendental equation. So you can see here like lambda square, it's a function of this psi1 and psi2. Psi1, psi2 are again the function of all this radius, angle. So all these are a function of radius, angle, height, all these parameters, and you have to solve this equation of motion. So in brief, if you have not understood something, the whole problem was to equate all 6 natural frequency. We calculated the natural frequency matrix, which is a 6x6 matrix, from the mass matrix and the stiffness matrix, and this were further calculated using the force transformation matrix, which was in term of function of all the geometric parameter, basically your radius and angle variable, and we equated all the eigenvalues of this matrix. Then what we did is just you write equation of motion, it will not give a solution. Now solving it is a challenge. So what we did is, when we equated all this and simplified the equation, this is where the observation part was there, and with our geometrical interpretation and using simple basic maths, we concluded that a 3D dynamically isotropic MGSP design problem was broken down into set of triangles in 2D space related by certain geometrical relationship. Now meaning to say, we had a 2 radii Stewart platform, and we wanted a solution that it should be a dynamically isotropic Stewart platform. So you can see we equated all these lambdas and all, and we got some conditions. So you can see this is when we simplified all the equation, we went on simplifying a complex equation. You can see this is a cosine rule, this is also a cosine rule. So based on that, we can say these 3 variables are forming a triangle, these variables are forming a triangle. So this area is related by this area by this. So it took a lot of mathematics to work out, and ultimately we concluded that a dynamically isotropic Stewart platform, the problem can be converted just for a solution purpose in a 2-dimensional space, and all the geometric variables, you can see RBI, RTI, alpha, alpha TO, all these geometric variables are related to a triangle. So meaning to say, once we get that side of this triangle, we can easily get the dynamic isotropic configuration. So there are multiple such triangles which will satisfy what we say as dynamic isotropic. Yeah. So this is the overall theme, and from this, once we get it geometrically form a triangle, we have got a closed form solution. So by closed form solution, you can see, so if I give a 12th class student also that I got a value of RBI, I got a value of RTO, RTI, he can just simply put in all the input variables and get the simple your variables. So now using our geometry based approach, we got a straightforward solution, we got a very flexible design, and we can also ensure mechanical feasibility. There's some yeah. So you can see here that here K and Q are basically the payload properties which are known to us. So if you are designing it for a particular variable, this payload properties are always known to us. So we can design our system accordingly. And once we have got the value of closed form solution, we can choose our design so that it satisfy our space constraint. So in spacecraft, so there are many solutions you can see. So this is a graph actually between all our parameters and leg length ratio. I can choose any of the configuration. I mean, if I take this line, say at 8 leg length ratio, so I can take this also, but here you can see there is some variable which is going to 500 mm. So in spacecraft, we have some space constraint also, that it should be within some 200 mm or 250 mm. So you have that flexibility. I think
All the participants are requested to kindly turn off their mics.
yeah. So as you can see that you can, I mean, whole purpose to study was that if someone comes with a different payload, or someone wants to design for a different space or design, he can always go for this general design. And whole PhD problem was, designing things in general. So again, we at the end, when you put all these equations, I mean, within all this natural frequency, you will get C omega 1, all this natural frequency was coming equal to 2k by mp. So we are able to design a system where all 6 natural frequency was equal to 2k by mp, where mp is the payload mass and k is the axial stiffness of each leg. Same way, we extended our study for right now. Whatever study we considered, what I showed you was when the center of mass was at the top platform, means center of hc height was equal to 0. But in real system, there will be some payload and there will be some center of mass height also. So the same geometry based approach we extended for center of mass height. Now it will have some center of mass height also. You can see phc variable. And just in brief, again we will get the curves, and from this curve you can see what design parameters you have to choose based on what is your space constraint, what are your joints limit, and all those things you can see, and then you can design your payload. So this was all the tough PhD part. Now coming to, I think now you can follow it much easily. Now it is much practical. So this was actually the background of the PhD problem. So now if you have not understood anything, you can come back now and see that whatever we got from our analytical formulation, same we put in ANSYS APDL. So ANSYS APDL is sort of, we do coding in that. And then you see this interface we developed, which has similar as analytical formulation. So we, in the analytical formulation, we assume that the top and the bottom platform were, so here also we have done it rigid. So each of the leg will be treated as say a spring. So each of the leg was treated as a linear spring. Payload center of mass was treated as a lumped mass. So when we simulated it in ANSYS, you can see all this natural frequency was coming equal to 30 hertz. And when we put the similar condition in, say, analytical formulation, if you remember, we got all 6 natural frequency you see equal to 2k by mp. So when we put back in 2k by mp, the similar stiffness and we around 30.46 hertz. So you can see quite similar results in when we worked it whole, like with handheld analytical formulation and with ANSYS also. So all these parameters which we got using our closed form solution, we imported it in ANSYS and we got the result. So we use a parameter called DII, which is dynamic isotropic index. So it's the ratio of the largest natural frequency to the smallest. Just it's a quantity to tell you whether how close it is to dynamic isotropy. So if all the natural frequency will be equal, the DII will be 1, because largest is also same, smallest is also same. But when you simulate it, it will be slightly, I mean, obviously there will be slight error. So you can see 30.60 divided by 29. So it was giving close results. So coming to the next part is, till now it was too much of theoretical and for academic interest. But when we go for application, when we want to implement in spacecraft, we cannot use conventional ball and socket joint and all those joints, because it will have friction, backlash, because lubricate and all those issues come. Once you send it to space, we cannot lubricate or we cannot prevent these issues. So what we do is, instead of a conventional joint, we go for a flexural joint. And using this, you can see there are certain requirements that it should have high axial stiffness, high shear stiffness, low bending, and torsional stiffness. So what is an axial joint? I hope you all know what is a ball and socket joint. So instead of that, we use something like this. You can see it is also giving you rotation in all 3 directions, but it is not based on some relative movement of one link with respect to other. Like you see in ball joint, one link is moving with respect to other, or in one link is sliding with respect to other. Here you can see it's a rigid thing. All are rigidly connected, and it's just bending. So the only disadvantage is there will be slight effect of bending stiffness, which we don't get in conventional joint. So we also did our simulation. So you can see now our model doing in application. So now instead of conventional joint, we included flexural joint. So when we simulated it, we got DII, means all the natural frequency were also very close. You can see. So with this we simulated with everything, and we were getting, means the last the ratio 1:0, which was so. That is why now purpose was, when you see the graph, you can see this is displacement in x, displacement in y, displacement in z. So what you can see, all the 3 curves are overlapping to each other. So this is a dynamically isotropic configuration. And meaning to say, what I showed you in pre-March, if you remember, that if you give a unit displacement to anything, it will first go to its resonance state, which happens with every system. And then after some time, you can see after root 2 omega, means if resonance is coming around 30 hertz, after some 40 hertz, you can see amplitude is going less than 1. So if at the base you are putting one unit and you are operating a camera at say 100 hertz, it will, if at base you are giving one at say 100, it will be around point only. So you can say that but if you would have not gone for a dynamic isotropic design, what would have happened if instead of this all three roommates who are having a sleep cycle now in NBH, someone would have come in this area and would have destroyed the whole purpose. So the whole purpose of study, that to align all the natural frequency at one place using this robot. And the other function was to decouple the modes. So you know that when it's a 6 degree of freedom system, one mode is always going to affect the other. So here, as you can see, I have given a displacement in only z direction. So you can see this is a curve for z direction. But if you see the excitations in other direction, I mean how much other direction excited, they are some 100 times or 1000 times smaller than, because this is log scale. So 10, 1.1. So they are excited some 50 less or 60 times. So basically, you can say that there is no cross coupling or no interference from the other roommate activities for our what if we are sleeping, our roommate is not disturbing us, the other person. So this is how came through. Then mode shape and all, I think need not to go through. And then through this, our experience, entire design process experience, we came across this Stuart platform, where this is the top platform, this is the bottom platform, and this is the payload. Basically, our reaction wheel is of 10 kg. So this is payload of similar properties as 10 kg reaction wheel. So we did the experiment in ISRO, and we designed a similar Stuart platform with a flexural joint. So this is a dynamic isotropic Stuart platform with a flexural joint. You can see this is a flexural joint, and this is the top side. This is a simulated reaction wheel, and we excited X and Y mode on a sleep table. This is a facility at ISRO they use for vibrating sleep table. And then electrodynamic shaker, we use Z axis, will measure Z axis, will measure XY axis, and rotational axis what you. And when you see that, you see experiment results also now, and you see all the experiment, all the things are. This is the whole purpose of the PhD, that you see damping. This is the natural frequency, all six are matching, and then your damping also it is matching. So obviously, I mean there are always because you are doing with hand, I mean close formation, and then you are doing, so it's not there, you are faking just you should always know frequencies are arising. Like say you can see in some okay, your simulation is going up and your experiment, you can see peak is going down. Why it is? Because whenever we simulate something in MCs or anything, or wherever, whether we do a closed form solution, we can never take into account the friction. We can do damping due to our dampers or damping due to other components, but we can never simulate the damping due to friction. But in real system, when you fix nut and bolt everything, you do it, there will be always be additional damping due to friction. So because of additional damping you see in the system, because your system has become more complex in the experiment, you see peaks is slightly less than the simulated, but it's still in the same range. You see if 30 hertz, then the resonance peak are coming at the same place for experiment simulation, but they have slightly different peak because damping will be different. Same everything in analytical, we have some different assumption. Like we said that our legs don't have any mass. I mean we had a payload mass, but legs we can neglect the mass. But in real system, leg mass was say 100 grams as compared to 10 kg of the mass. So it was neglected, but it was not fully zero. So that is the reason we got some 0.5 hertz of difference, and there are many other reasons. So I mean our results are very encouraging, but we should always know if it is deviating by small quantity also, what are the reasons, because it will always do. And this is the damping model, as you see our how our curves are over in experiment. When we did something, how it is matching with the experiment. So this was my entire PhD. later on, just in brief, on we extended study to more than 6 lakh. And why it is important? Because now I have designed a 9 kg, but tomorrow ISRO will come and tell you that you design a system for 15 kg. So if I put a 15 kg of payload on my previous configuration, it will won't give you dynamically isotropic configuration, because we have studied this problem for so long. Why not? I mean, just because if your payload is going heavy, then what you intend, just fabricate 1 2 extra leg and then do some reshuffling, and your previous whatever 6 legs you have fabricated, means I have 6 leg, I will make use of same 6 leg and maybe fabricate 1 or 2 extra leg and then construct a Stewart platform with more than 6 leg. And in this way I can distribute heavier payload. I mean, it was not sufficient to distribute heavier payload. So in future, if I want to extend it to 7 leg, 9 leg, making use of previous legs which I have already fabricated. So now I have to only fabricate 1 2 extra leg and reshuffle. So I studied that. You can see here 8 legs are there. So 4 in the inner radii, 4 in the outer radii. Same way here 9 legs to a platform, 9 in the inner and 9 in the outer. So this study we did that in future we will extend it, and same way all the studies we did, and we also validated it similar way which we did for 6 Stewart platform. Here also you can see closed form solution, and for 3 basically means 6 leg Stewart platform, your results are matching. For a 7 leg Stewart platform also your results are matching. So it's general that we have extended this study. And in future what we plan is, right now our setup is passive damping. Basically we have used passive damping. In future we want to extend it to active control. Each of the leg have sensors, and each of the leg will have piezoelectric actuators. So we can do it. I mean, it will give but one thing we have to remember is, when we do an active control, take it to space, we will have to figure out electronic components. It will be expensive, first of all, because we are using electronic component. The second thing is, you are carrying data acquisition system and all, then that also will have significant weight, and then you will design a control system that will be another challenge for you. So what we have done in our PhD, that whatever European Space Agency and other people have done in the Stewart platform, they have not used a dynamically isotropic configuration, and they have used active control in a simple configuration of Stewart platform. And whatever they were getting results from their active control, we have got a comparable result from passive control, which is much cheaper. So with dampers and all those things, we don't require any say electronics component, and the same results we are getting with a passive setup where we are not needing any electronics component. But if you use active control and go into dynamically isotropic configuration, we are going to get even better results. So this is the whole idea of my PhD. Just in brief, we are currently, I mean, just off topic, but there are many biomedical students also. So we are currently the same Stewart platform. It has many applications, right from spacecraft simulator to many other applications. Like even James Webb Telescope, you see, there are, I think, some 40 Stewart platform which is used for point, because it's a 6 degree of freedom system. So if you want to point it something in 6 degree of freedom system, everywhere wherever antennas or mirrors are there, at the back end you will see a Stewart platform. In the James Webb telescope also. So Stewart platform is one of the parallel robotics, and I worked in the area of parallel robotics. So this orthopedic problem was basically, if you meet with an accident and your bone has deformed into 2 pieces, basically you can see here X-ray images. So the bone has gone into 2 pieces. So how to return? I mean, it has been 6 degree of freedom. It has rotated also. It has twisted also. It has translated also. So we cannot see it. So we have built in such a way that we have written a kinematic equation for this robot. And what doctor will do is that doctor will just go and fix this leg, fix this robot in the leg of the patient on day 1, and take 2 X-ray images. From the X-ray images, we will interpret that how this 2 points is located, how much far, and day by day it will come and align. So this is the whole idea of day by day prescription will be given, and day by day it will be automatically aligned, and it will become, you can see, linear. I mean, bones will align. So this is the thing we are in, and this project probably in next 1 2 months we'll wind it up. So this is the list of publications which we got from this work. And after completing my PhD, I recently joined as a postdoc in I3D lab, which is because I worked a lot in mechanical department. This lab is more mainly based on computer science, computer vision, AR, VR, multi-robot scheduling. So I am also learning and expanding my domain, and I am working under Professor Biswas now. And you can see in our lab, Ajit Krishnan, our astronaut designate, he did MTech from our lab. So technical part apart, I think I'll take 5 minutes more to tell you something which is really significant for you. And all this journey, all this environment which I showed you for IISc, and all the design process, the PhD process which I told you, most important question is the opportunity in academia, and basically how can you be the part of IISc and IITs. So if you want to go in research, the first thing you should figure out is whether you want to go in academic research or industrial research. Basically, if you go straight away want to go in ISRO, DRDO, and in ISRO, DRDO, basically you work on more practical aspect rather than going more fundamentals, and basically you work like a project. So what you saw, I say I worked in formulation, then I worked in FEM, and then I went into experiment. If you go in ISRO, DRDO, you will just go in directly to FEM formulation, or you will go in experiment. But while you are in academia or doing a PhD, you will work with the background of the problem. You will generalize the problem. You can tell what is actually working with the system. And nowadays a lot of AI ML has come into business, which doesn't, the people who are using ML don't know what is actually happening in the system. But being a robot design engineer or a robotist, we always make sure that we are having complete knowledge of the system. So if you are going into academia, you should have a quest. You should have a quest for fundamental knowledge, and you first thing is to decide what kind of research you are going to do, and then you have a lot of time. If you want to go into research, whether first if you are not sure you want to go into research, then you go to a 2 year or 3 years course, which is MTech research, MS. If you are not very sure, if you are very sure, if after your MTech, if you are sure go for PhD, then you go for an MTech, then you continue PhD. But now a new scheme has come, I think from last 7 or 8 years, which is something called a direct PhD. And if you are very sure for your PhD, you can always go for a direct PhD in any of the IITs or IISc. Good thing about a PhD, direct PhD in IISc, is that you get your MTech and PhD degree both. So I got and PhD both in IISc, while in IITs you only get a PhD degree. So there's not what you can think from your part, that if you are not, you have to first study 2 years of MTech, then 5 or 6 or 7 or 8 in IISc. We have people who have MTech also and doing PhD from 10 years. So first you have to figure out your MTech project, do 2 years of MTech somewhere in IIT, then come to other place, do 5 years or 6 years of PhD. Rather than that, if you are very sure, you can directly go direct PhD. So for me, it took 5.5 years to complete my all my direct PhD. But it depends on your skills, your project, how your is working. I mean, I've seen people finishing in 5 years. Also, I've seen people hanging around in 10 years. Also, it all depends on multiple things. So something that I would like to announce is that this year onwards, previously it was that any person in NIT, IIT who have a good CGPA more than 8, they can directly apply for interview for a PhD program through central, means all our IIT, they are part of centrally funded technical institute. And before, prior to this year, we had only a PhD where you can enroll from, but from this year you also have an MTech program where you can do MTech also using CFTI. So generally for getting into IITs during my time, the gate rank was less than 15. Because they are taking interview now, you get around 500 or 1000 rank also you get. But if you can't get 1000 rank also, if you maintain a good GPA, you can directly call for an interview. So basically what I mean to say is always there is possibility of giving for an interview for MTech or PhD. But from this year, IISc has introduced CFTI mode, and basically all you have to do, because if someone is in their first year, second year, all you have to do is maintain CFTI mode. I know in an IT it may not be a tough task. Plus, if you are around hanging around in the border, if you are in sixth semester and hanging around in 7.9 or something, try pushing your CGPA to 8. It will be helpful for you in all the IITs. Or if you want to go to research, you have to keep three things in mind. First thing is you should have a better grade. So 8 or 8.5 is minimum, but if you have something like 9 and all, that will always your academia, the quality of student you are. I mean, you are sincere, that it will reflect. And even if you are applying in foreign university, it will always help you out. You have to build a research profile. I mean, you do your internship, research final year project nicely. Some, if possible, you write at least a conference paper or present somewhere. Always be involved in other projects like you do in your innovation. And the most important, the toughest part of getting institute like IISc or IITs or ISRO or DRDO is not the exams, but the even tough part is the 1 hour or half an hour interview that it's basically not an interview, but it's basically a torture. Sometimes they will not send you out, you yourself will move out of the interview, because around 4 to 5 people, scientists, and they are all blackboard type interview. If you are aiming for a research, and if you are preparing gate or something, you will always formula, you will learn formulas and all. But if you are targeting something, a research interview, you want to crack a research interview, you should practice derivation, you should know all the assumption. If you are learning knowledge theory, about, you are just doing v square by 2 or something like that. You are knowing from where those terms are coming, whether it's for streamline flow, what are the assumptions we have taken, 4 5 assumption we have for Bernoulli's theorem. All those things at least you should know. So the background should be clear, and that will help you out in interview. So whatever subject you are reading now, have a background knowledge of that, how the derivation is coming from, energy conservation of energy. Many times we forget that derivation and formulas when you go in the interview, but you tell those in the interview, you tell the basics in the interview, that also they will consider. So it happened with me also. But all the basics, because I do 95% of the basics, that even if you tell 60 70% of the basics, you will get through this interview. So this is the whole idea. And regarding maintaining your profile, I would recommend you to align yourself in one direction. It's always good to learn many things. I mean, whether it's Python or everything. I see many people who do their internships in, say, data science, then final year project in robotics, and then some they will take some project out of interest in some other field. I would always you to align yourself in particular direction. If you are looking for a design or robotics, so everything you, this is you have some level uh, diversified. So you learn many things, but when you do something, try yourself, because there are a lot of opportunity around. So wishing you good luck, and thank you for inviting me. And non both the questions, I'm happy to take.
Thank you, but sir, insightful. It just sparked a lot of follow-ups. So for you can raise your hands. Rahul Sharma, you can proceed with your question.
Is my voice audible?
Yeah, I can hear.
Very good afternoon, sir. Question is, when the vibrations were not identified in the spacecraft, what problems initially were encountered, and what were the potential problems were thought that these may be the problem due to which the spacecraft getting encountering problems?
Yeah. So as far as vibration part is concerned, so see, there was a term I used. There's a micro vibration which is in the range of 1000 micro G, and that is up to 250 hertz. These are all experiments, and there's a separate study that people have done in the past. That spacecraft works, if you have a system, if you have this device, is coming. So my problem was not to get into what is the vibration. My problem was that this much vibration is coming, and this exists in the spacecraft, and this we have to mitigate for our system. So in existing literature, as I already told, so my literature, so my thesis was reviewed by Europe, one of the person from European Space Agency, and you won't believe his steward platform actually has flown in space and come back. So he was the right person to review my thesis, and he gave an excellent grade to me, which means that he also loved our ideas. Because what I mean to say, just tell you that what will happen in his system, that he also built a steward platform, but his say one natural frequency was here, one natural frequency was here, one natural frequency was here, because he had not designed it for natural frequency. So say I wanted a region of isolation. So in vibration, this down part is there, no, this slopey part. This is the region of isolation in vibration. So I wanted to operate in this part, but in his configuration, what it will happen, that if suppose you are getting a vibration isolation of minus 40 dB per decade. So in sound vibration and in control system, we use a term called decibel decade and all those things. So this is basically 10 theta, you can say this slope of something. So in actual, if you use a 1 degree of system in active control, what he has used, you will get minus 40 dB per decade, right? This slope you should get in active if it's a single degree of system. If it's a single degree of freedom system, you will get something like this. But because you can see other peaks are coming and disturbing this part of the peak, he was not minus 40, he was getting around minus, I think, 14 dB or something, or minus 17 dB. So you can, he was not getting the full vibration isolation as you should get for active control. That is because he on control part, and he has taken a conventional data, he has not seen the peak of other degree of freedom. But in case, if you see all the, this was one of the peak was also coming here, the other also coming here. So the region of isolation, so this was a very quiet region in my case. And even though in active control, even though it was a passive control, so what happened, I'll just tell you a brief about active control. So in active control, if you do, you get more slope, while in passive control, when you do, you get less slope. Just in brief, so slope will be less. But in our case, even though we have used passive control, our result was better than their case. That is because we have used a dynamically isotropic configuration. So we were getting around 18 to 20 dB per decade. So it was better than them. That is because just we have consolidated all those peaks. So this was what has done in the past and what we have done.
Anybody else who wants to ask the question can raise their hands.
I think Rahul has another question. Yeah, Rahul.
Sir, actually, I want to ask that let's say sensitive equipment, let's say camera is mounted on the spacecraft, and due to operations, it is we are getting a blurry image.
Yeah.
Okay, so just for the camera part only, I'm asking that whether software can be used to remove those blurs or not.
See, there is a limit over which the software can be removed. Whatever image I showed you, know, you remember the first image, which was one image without isolation and what. So all those filtering and image processing, everything works, right? But at the end of the day, just understand the intensity of the problem. So you have something at 400 kilometers, okay? So something is lying at 400 kilometer, and even if by micro radian your things are moving. So if you do 10 ki power r theta, you do something like r theta, in downward side, one micro radian and a 400 kilometer, it will say 400 will go by 40 meters. So the things will oscillate by 40 meters when you see Earth. So this is the intensity when you are doing something from 400 kilometers. So there are techniques. You are right, but obviously, if and it's not about only camera or something. You are only talking about camera, but it's about many sensitive equipments also who are operating in the range of 80 hertz, 100 hertz. There may be some communication link which don't want any disturbance. So all those have to be kept in the quiet region where we have designed. So it's not about only camera where you can apply any image processing techniques, which will not work. In camera also, there's up to a level over which you can do image processing, but over when you are doing imaging or you are doing it for defense, want very high quality image, or when you are doing it for communication or other payload, you want the payload to be less sensitive to radiations. So that is why this technique is used. And you can also ask any general question related to MTech, anything? Yeah, Keshav. Yeah, Keshav, please go ahead.
Hello, good afternoon.
Yeah.
How does the micro vibration isolation system work? Actually, how it controls the vibrations?
Basically oscillating in space. Right? Now we have mounted it on our Stuart platform. Okay. Say it is I'm it vibration it is in. It is inducing amplitude vibration. Okay, so using our system, which is now a degree of freedom isolation system, so it can work both way. If you give unit amplitude downside, it isolate upside. If you give something up, it will isolate downside. So basically, this is a interface. You see, this platform is an interface. This source, this reaction wheel, which is rotating at high speed, and because it's inducing vibration, if you give, suppose it is giving you amplitude in some direction, it may go down to say, it will go down to some 50 times or times when it reaches to the base. So this is the whole idea. Same way, if this some camera is mounted instead of this, we do some experiment with the camera and design our Stuart camera. Vibration coming from the base, you can spacecraft bus is there, the base. From there, if one unit vibration is coming, it damped by say 150 times or 100 times, something like that. So meaning to say, it works both ways. This is a setup and interface basically. So this is, see, this is a system. So damping, basically this is what basis of multiple damping. Hysteresis damping. So if you directly mount this on spacecraft bus, take this momentum wheel and mount bus, keep this interface. You are giving one amplitude, your space bus will also oscillate by one because connected rigidly. When you have brought this interface, oscillating in all six directions, whether torsion direction, rotation, or translation. This is the whole idea.
So, what inspired you to work on vibration isolation for?
First thing is the PhD thing is selecting a guide and selecting a research topic. I think it's most tough part, whether you want to do PhD from India, you have to see who works on your domain, and then you have to take his feedback. I mean, how many guides, you go anywhere, you take the feedback of the how the person, the guide is. Obviously, everyone goes behind the technicalities, but you have to also see that whether someone who is working with you, whether you can work with him for next 5 years or not. So what inspired me is the first thing, as I showed you the Venn diagram. If you see in aircraft, right from the second year of my BTech, when I started with structure of aircraft, structure of helicopter, then structure and fatigue group, which I worked with NAL. Then I worked in designing a vibration test setup for ISRO, which I showed you. In my final year project, I did laminated composite under Nitin sir. So basically, if you see, everything for me was around design field in mechanical, not in thermal or industrial or any other. And it was mainly along vibration. When I came here, I saw something which in robotics, vibration, and design. So it was my field and my interest. So basically, that whole intersection which I showed, that because I had a profile of that, I was very clear that I had a basic knowledge of the subject, and if I get this, I learn, I can flourish more. So that was my basic idea. Hi, Ansh.
Good afternoon, sir.
Good afternoon.
Sir, as you said, there are future scope of active vibration control in a dynamic isotropic MGSP. So do you think, and as per your experience, will it be more effective? And what desired result do you expect from using active DAM?
What desired result? Desired result is, yeah, I understood your point. So right now, is there the slope in a passive control. Okay, so what was happening previously, they were implementing active control, but they were not getting slope because, as I already told, that their other slope was interfering with region of isolation of the particular but when you with active control, so with better to say, let's say there is a unit to this point, you can here if you say it's a unit less than that, you will get more isolated, which I want to get into. Meaning to say, you will get region of isolation and more here you basically determine that. So less in the region of more less region of isolation performance in isolation. So you will probably get around 30 to 40 because they have dynamic isotropy. I'm sure that. But again, you have to consider that electronic components will come, control system will come, mass will increase because type system which you are using. So mass is a critical factor. Then power factor. In spacecraft, there is always a fight for microwatt and milliwatt and grams. In space, each gram is like gold. So there's a fight for everything, and you have to optimize your system. So if you are going for a to also keep it other aspects of. Yeah, Rahul.
What are the platforms of an piston or some
Saying that legs?
legs?
No, they were not pistons or something because if you want actuator, then obviously you need electronic, and there was no moving part, so there is part in that. And if you put a it will work, but again you have to design the damper in that way. Right now, basically on any but if you use a fluid, right now we have 6% damping, but if you use any fluid or something in the lab, you get 30% damping. But apparently will basically the peak, that is the peak, that is the reason of more damping. But basically you are concerned with only the region of isolation because your instrument are operating at this region. So right now our setup is material damping. So any material, whether you take aluminum or any material, they will have an inherent damping. So aluminum has, I think, 0.02%. But when you put in it in something, it will give around 4 to 5% of damping. So that is what. Anything else? See, AI, obviously, people in my lab and other people in my lab. See, I showed you three types of approaching a problem. The first was I approached it analytically using equation of motion and all. The second I showed you using FEM, and third was your experiment. You can the other use some technique and then generate those results, or the other can be you use AI or neural network to generate those results. So you can always pick my paper from MMT and try it in basically in AI. But you can always do that, and there is no harm also. But again, the novelty of this problem came because it is a dynamic isotropic problem. So the complexity of the problem was reduced because a design point of view, because we designed it from the scratch, and we designed each and every leg of the robot. We like, if you see, there are many robotics lab in and around the world. What they do is they are given a robot and they will take reading out of that using AI ML. They publish paper and they get good paper in 3-4 months. But for someone like us who work in the core area, so they cannot come and teach a student what is robotics. It would be very hard because they don't know what is actually happening in the robot. But people like us who have worked from the base, developing from equation of motion something, so we know entirely the system knowledge. And once you know the system knowledge, I mean, you know the fundamental part of the robot, you can always go with AI ML if you are concerned with industry part or something application, and you can use it as a tool to validate something or for your application. But for something related to space or something, you have to be confident that how your system is behaving. So because I also read that there are legal, if say you build a robot out of AI ML, and if a robot goes and harm your say operator, then you who will take the responsibility of that? Because you don't know how your robot is going to, because you have trained that robot, not basically you don't know that robot from the heart. But people who are from design background, robotics and design background, they will know robot from heart, and they will know that how, if length of this link is this, length of this link is that, the how, where will my end effector be. So when you know everything about the system, you know about the robot, and nobody can question you out of that. So AI ML for me, I mean, even I am also getting into that domain, but the first thing that you should do is obviously focus on fundamentals and learn AI ML as a skills and as a validatory tool, like you do for FEM. Yeah, Rahul.
Sir, platforms, two radius system was there. Let's say if in their search more than two radius system, let's say three radius or four radius system was there on the platforms, will it be better than the two radius system, or the two radius system is the best?
See, first thing is the moment you use three radius, no, your configuration will become unsymmetrical. Meaning to say, if you see our system right now, if you see two radius, where it is, yeah, you see two radius here. You see all the three legs are 120-degree apart, right? And this blue legs are also 120-degree apart. If you use four leg also, they will be 90-degree apart. So the whole idea is that at least there is some sense of symmetricity in the problem, right? The moment you use three radii, you see somewhere you have to compromise, because in one of the radii two leg will come or one leg will come, then the problem will no longer be symmetrical. So analytically, first thing is analytically it will go complex, and second thing is that two radii is, I will, three radii you can still achieve dynamic isotropy. The advantage you will get is you will get more configuration space. I mean, the design, you have say some 1 crore configuration we got in right now. In three radii you may get some 10 crores of configuration. But because you have given a flexibility and additional variable to your problem, say now you have three radii instead of two. But because we are getting sufficient space and all, and two ready design space, by space I mean design space, that we have multiple solutions, we can select any one of them. So there is no point of going and complicating the problem. But yes, you can achieve dynamic isotropy to three radii also. Ultimately what will come, for some specific cases, the three radii will merge to two radii, that will give whatever configuration solution I have got, and you will get some additional solution, I mean with three radii. But there will be one of the solution where two radii will merge to form single radii, and that will give my solution. So you can always take four radii, five radii, six radii, but complication will increase. Yeah, anything else? Yeah, Anmol, yes. Yes, Anmol. I can't hear you. I think you are unmute. Keshav and Anmol.
Hello.
Ha, Keshav, tell me.
Sir, what are the main points we have to consider during the designing of micro vibration isolation system?
Main points in the sense? See, if you are
Like weight and thermal compatibility.
all those things. See,
Like
you are talking about application, right?
Yes, sir.
See, first is vibration, what range it is operating, what range you want isolation, first thing. The second thing is what are your payloads and how sensitive are they in what region. So say camera is sensitive at some 80 hertz or 100 hertz. So it also depends on what payloads you have. Then what is your load? I mean, because there are launch load also. When you launch something in spacecraft, as I told, it's not going to be 1G, it is going to be 10G. So because of which your joints should be strong. I mean, when you have launched it or when you have done the experiment right now, you have done in 1G, but when it goes in space, that whole payload, no, it becomes 10 times more heavier. So whether your joints and all should not break. So all those comes under design part of that. And thermal aspect, I don't think thermal aspect should be a big issue, because as I told, I have not used any fluid or something that is going to freeze or something. And second thing is it's a very rigid system. So I don't think aluminum, there should be some problem with, because aluminum is already aerospace material which we use for other components also. So aluminum alloys we already use for other components like titanium, aluminum, all those things. So there should not be any thermal problem associated with it, but it will come if you use some fluid or some sensors and all. You should check it in that thermal environment also. But as of now, I don't think aluminum as a aerospace material or in those environment should create any problem. Yeah, Anmol.
Hello. Good afternoon, sir.
Good afternoon.
Sir, actually, I want to know that, like in robotics, we have all subjects like mechanical, electronics, and computer science. So basically, I am from electrical engineering. So I want to build a career in robotics. So what should be the roadmap, or how should I start from here?
Robotics, as you told, no, it's very challenging field right now, because it is one of the field where even in my lab different 3 to 4 domain people are working. I mean, computer science person is also working on same robot, a mechanical person is also working, and electronics people is also working. So as a mechanical engineer, we work more on, say, design and control aspect, a bit of control aspect. Then as an electrical engineer, I see they work on more on control, or say autonomous part of that control aspect. And then computer science people work on vision and all those things. So meaning to say, there are, so the robotics domain has diversified into, many subfields. And even I am expanding day by day. Even I am learning. See, I am not an expert in AI or something, but from two months I am in this lab, and I am also hanging around with computer science people. So I am also learning. So for you, because you are from electronics, electrical background, something related to control system or AI will be good. I mean, as per your application. But if you want to go to academia or something, so you will have students who are working in different domains. So I think at some point of time you have to expand. Like, I am also learning things, because if tomorrow I go and guide few students, I mean, now also I have many PhD students. So when they work, at least I should have a superficial knowledge what they are doing. I cannot have that much deep knowledge which I have in mechanical design and the parallel robotics or Stuart platform. That much deep is not required. But at least if someone is doing something, I can understand what he's doing and what approach he should or she should take. So you should focus on one area only. But apparently robotics is too big to take up. A single person cannot take all robotics, that I can understand. But at least one area like control or AIML you take, but you should have basic knowledge of mechanical aspect also, and all those aspects to be a good robotics engineer or scientist. That is the.
Okay, sir. Thank you, sir.
I hope we have no further questions. So moving forward, I would like to cordially invite our visionary, our faculty in charge, respected Dr. Saurabh Gupta sir, to enlighten us with his words of wisdom and motivation. So.
Hello, am I audible?
Yes,
Yes,
Am I
Dr. Sir.
audible? Yeah, okay. So yeah, thanks Yogesh for this wonderful talk, and I think the students must be feeling very motivated and charged up after your this. As the future is also space tech, and we are lucky to have one of the alumni of IIT Raipur, which is so closely working with ISRO and other space tech things. So I think other students should take this as a good platform and opportunity. And I don't know how many of you know, but Yogesh has also started a rocket club in IISc that he told me when I visited him 2 days back. So I think if interested, some students from NIT Raipur can take this initiative and they can get guidance from Yogesh to come up with the rocket club. And we all know, we all are fascinated with these deep tech technologies that are coming up in space. And as government of India has also opened the space for private players, for startups. So I think this is the wonderful opportunity to for students who are excited to do something for country and maybe for their future and whatever they want to do. So there are a lot of opportunities, and this is the total new domain in India. And as my last visit, I visited to IISc, and then I also went to ISRO and met there some people. And Yogesh must also be knowing that there are still a lot of areas that that in which still India doesn't have any expertise. So even if you will solve the low-hanging fruits, like low-hanging problems, small problems in space tech, then down the line, like in 3 to 4 years, you can definitely make a very good career, whether as an entrepreneur, whether as a if you want to go higher studies, like in any field that you want. Fine. So I hope this is all from my side, and thank you, Yogesh, again for your wonderful inputs. And we will definitely we want your help to connect us to more people who are into different domains
Yes, sir.
and different areas of space tech. Right? Like bioastronautics is something that is really new because India is still working on Gaganyaan and
Yes, sir.
a lot of scope for biomedical engineers, biotechnology engineers, people who are working on health. Fine.
Yes.
So these are all unexplored areas. I think students should take interest, and let's see how we can move this to center for space and interplanetary exploration. This is a very new thing for all of you, for students of NIT Raipur, and I think with your support, we can definitely NIT Raipur can definitely contribute in the space exploration of India. Right?
Yes. So
So
I would
yeah,
really expect that next time in ISRO Rover Challenge we put some rovers, sir. That would be a good
yeah,
start for the club.
definitely, definitely. So I think the young students of NIT Raipur should take this vision of Yogesh
Mm.
that some rover should come from NIT Raipur,
Mm.
find some rocket some satellite should come from NIT Raipur, and this is not at all difficult when Yogesh is there to guide us, and he has a good network. He can, and like I think most of the students can. It just need your motivation and your excitement to do things and to build something to solve problems. If you have that attitude, then definitely NIT Raipur can play a bigger role in this space journey of India. You know? Fine.
Yes.
So Yogesh, anything you want to say now?
I think, sir, I just want that all of them remain motivated, and within next 5 6 months we see a lot of projects that they take up, and as per their expertise. And I think rover would be a good way to start because rover problem will have design aspect also, electronic aspect also, every aspect will be there. So right from doing biomedical experiments in the moon rover, everything will be there. So if something like that they take up, I think they will, like they get for Baha and Supra, they get local sponsors at least small. For rover challenge also they will get sponsor also, and if they get to get with ISRO, they will get good name also. I mean, ISRO is a brand value. So if they target for next year URC, I think it's a good, because it's a project. So I think they will be able to take up. And I have also worked with rovers, so if they need it, I'll guide them. So not an issue, but someone should take up.
Right, yeah. There should be the pull from inside NIT also, and push from inside NIT also, and Yogesh is always there to pull the things up.
Okay.
Fine. So I hope it's all under like innovation cell and all that. So whatever the innovations you want to do, you can channelize to space tech, maybe for next 5 years, and we'll see how it goes.
Yes, sir.
Fine.
Yes, sir.
Okay.
Thank you all. Thank you,
Anything,
sir.
anything? Anybody want to share or something? Okay. Okay, then we can end uh, the session now. Fine, Yogesh. So we
Yes,
will
sir.
try to catch up you again. Thank you, everybody.
Thanks. Thank you all.
Thank you, sir, for your words of wisdom. Thank you, our esteemed speaker. Thank you, sir, for coming. This session would have enlightened a lot of knowledge among us. Thank you, everyone, for joining.